Hey, what's up, everyone? How is everyone today? Good to hear. I'm guessing Achieve did not continue to give people trouble yesterday. That's good. By the way, whoever suggested putting the hash brown in the sausage McMuffin, not bad, not bad. Tried it today. Good call. Plus, you can get them together for $2, so it's nice. Okay, lecture's just becoming a McDonald's commercial now. I should probably stop. It is quite a deal. It is quite a deal for my poor grad student self. Shamrock, I've never tried the Shamrock Shake. That's like mint, right? Not a big mint shake guy, but they're so good. What are they? Is it just it's like Oreo mint. It's oh, too much mint sometimes. Interesting. Yeah, it's one of those things. It's like that's like one of those things everyone raves about that I've never tried, like freaking McRib. Although honestly, I've never actually heard anyone who really loves McRib. Everyone's like, who is clamoring for this sandwich? Not a big fan. But yeah, I've never had McRib either. Don't know. Anyways, should probably talk about some math here. Okay, so today we're going to cover chapter 13.1, and we gotta get a move on because first exam is not next week, but the week after. On what day? On Tuesday. On Tuesday, and it's going to be over. It's going to involve material, which we have to get through by the end of the next week. And it's chapter per day, so we gotta get moving on this stuff. Okay, so 13.1, just kind of introducing the functions we'll be dealing with for the next several sections. So vector functions are vector valued functions. It's through Canvas, yes. Correct. Yeah, if you've taken a math course in the past couple semesters, then it's probably going to be a similar thing. And when we get closer to the exam, we'll talk more about exactly how it works. But yeah, it's just going to be through Canvas. There are going to be time slots throughout the day. I believe 3 different time slots throughout the day where you can take the exam. And you'll have, I think it'll be last semester, so it might have changed a bit this semester, but yeah, we'll talk more when we get to it, but like an hour and a half block each. So if you're in a, you know, unfortunate time zone, you can hopefully find something that works for you. And you'll have 45 minutes and time that inside that hour and a half to, or actually it might be, we'll look at the details, but you'll have a bit of time inside that to do your thing. And then you'll have like 10 minutes after to upload your work as a PDF file, which we'll talk about also later. But it's all going to be done through Canvas. So yeah, it's I mean, it's not next week, it's the week after, but it's Tuesday the week after. So it's like a week and a half away. Correct. Okay, anyways, vector functions or vector valued functions are what we're going to be looking at. So here's kind of the setting. So imagine you're in space. And once again, you're a particle traveling along some curve in space. Call the curve C, because why not? So suppose you're traveling this direction along the curve. And so at a given time t, you're at a certain point on your curve. So at a point, at a time t, particles at a certain point, we'll call it x of t, y of t, z of t, right? The point the particle's at depends on the time t, and you can write the x, y, and z coordinates of the of the point the particle is at as a function of time, right? So you can keep track of where the particle is at time t, and you can look at each coordinate separately, and each of those is going to be a function of t, right? Your x coordinate at time t is this, your y coordinate at time t is this, your z coordinate at time t is this. And when you put them all together, that's the point your particle is at time t. It's moving along this curve in space, in time. So it'll be convenient to use the language of vectors. So instead of talking about the point, we're going to talk about the position vector for the point. So remember, that's the vector which starts at the origin and ends at that point at time t. For reasons unbeknownst to me, we always call that r of t. And so this is just the position vector for x of t, y of t, z of t, the point. So that is the vector x of t, y of t, z of t. And we call this r of t for shorthand. So this is a vector valued function. This guy here. Hey, buddy. So it's you input a time t. So remember, function is you input something in the domain, it outputs something in the range, right? So you input a time t. This function is going to spit out a vector, x of t, y of t, z of t. And that vector gives you the position. You think of it as your position on the curve. And so this guy is going to trace out the path of your particle on the curve. Right, so at different times t, you get different vectors you get vectors ending at different points on your curve, right? And it's going to trace out, you're going to get these vectors tracing out the path of this particle in time as you move along here. Are there practice exams? Yes. I will send out some emails after class about that, Terrell. Okay, so in this case, T is, we call T the parameter. Right, so we usually think of T, we usually call it T because we usually think of it as time. But T is the parameter here. It's the thing you're inputting into here, and it's outputting your vector. The first one will be next week, Sarah. I will send out info about that also. Sorry. So X of T, Y of T, and Z of T are the component functions of our vector value function, R of T. Right, remember R of T was just the vector X of T, Y of T, and Z of T. Each of those is just a normal scalar function, right? Like T squared plus 1, cos T, e to the T, that kind of thing. The type of vector or real valued functions that you're used to dealing with so far. Those are the component functions. So often we're going to use vector valued functions to study these curves. So sometimes we're really just interested in a curve, right? We want to know things about this curve up here. Right, so we just have some curve C. We want to know some things about it. We want to study it. And so what we do is we look at a vector function which traverses this curve, right? Which traces it out. So it's a curve we're interested in, but we're going to use these vector functions which trace them out and calculus on these guys to study them. So we say, let me say it this way. So we say a vector function R of T which traces out a curve C so we say that function parameterizes the curve. Right, so we have a curve, we find some function, R of T, the vector function, where as T varies, the tip of these guys is going to trace out our curve. So you can think of it as giving you the position of a particle along this curve and time. That's going to parameterize your curve, right? So that tells you a way to move along your curve, right? So you can move along at different speeds you can move in different directions along the curve, and you can be at different points in different times. All of those are ways to parameterize the curve. So there are infinitely many ways to traverse a curve, right? So I could be here at time 0. I could be here at time 1. I could be here at time 2. I could be here at any given time. I can move in this direction. I can move in this direction along the curve. I can move fast and slow. I can move at constant speed. There are infinitely many ways to move along these curves. So there are infinitely many vector functions which will parameterize these curves. So I want to emphasize that. So there are infinitely many ways to parameterize a given curve. Right, and those correspond to different ways to move along the curve, different speeds, being at different places at different times, moving in one direction as opposed to the other direction, etc. But all of those parameterizations are going to trace out the same curve. So let's look at an example. So this is a very common curve and parameterization we're going to see. So suppose we have the vector function cos t, sine t, t. Suppose we let t go from negative infinity to infinity. Usually that's what we assume for t. Sometimes we'll restrict it to get just a piece of a curve, and sometimes it won't be defined for certain values of t, so you have to exclude them, but we won't worry about that too much. Okay, so this is a vector function. This guy is going to trace out a helix. So at t equals 0, so at time 0, we're at the point, plug in t equals 0. You get 1, cos of 0 is 1, sine of 0 is 0, 0. So 1, 0, 0. And then at 2 pi, or we could say at, let's say pi over 2, we're at cos of pi over 2, which is 0, sine of pi over 2, which is 1, t equals pi over 2. So we're at 0, 1 pi over 2, and et cetera, et cetera. So what's going to happen is we get this helix. And just to emphasize, so we're moving in this direction as t increases. And I don't have time, but usually I like to sort of go through. I like to see if we can figure out what exactly this vector function parameterizes. But I'll just kind of explain how you would figure this out yourself, right? So it helps to kind of look at what's happening, say, if you're just looking down on this in the XY plane, what's going on with this? And then sort of piecing things together. So if you look in the XY plane, so if you ignore what's happening in Z, right? So if you sort of smash this down on the XY plane and just look at the X and Y coordinates, right? We have cos t sine t. So if you're looking sort of down on this and can't see what's happening in the Z direction, if you remember, cos t sine t and the XY plane. So this does give you points on the unit circle. And and we're going to be traversing the unit circle clockwise, or counterclockwise in this case. Right, so in the XY plane, we're constantly going around counterclockwise along the unit circle. So that's what's happening in X and Y. And then Z is just T. So Z is just constantly increasing in time, right? So we're going around in the XY plane. And in the Z direction, we're just going smoothly up. And so that's just going to trace out this helix here. So that is something we're going to run into a lot because it's a nice example that's sort of easy to visualize, relatively simple, but not too simple. But that is an example of a parameterization of the curve there. Okay. So one thing we're going to be interested in is some curves we'll be interested in occasionally are the intersections of surfaces. Let me say it this way. Nah, that's fine. Parameterizing the intersection of two surfaces. Right, so suppose we have two surfaces. So for instance, suppose we have like this circular cylinder and this plane, right? So these guys are going to intersect each other in a curve. Let me use red to represent the curve of intersection here. It's sort of going to be this this tilted ellipse here in this case. And so often we want to parameterize curves of intersection. And of course, there are infinitely many ways to parameterize a curve. And not every two surfaces you're going to be able to use either of these. But they're basically, for everything we're going to give you, they're going to be like two strategies for parameterizing the curve of intersection of two surfaces. So the first one, so we use an example. So suppose we have the intersection of the surfaces. So the intersection of the surface is given by the following equations. So x squared minus y squared equals z plus 1. Z minus 1 doesn't really matter. And the surface x squared plus y squared equals 4. Okay. So many ways to do this. The easiest way is the following. Notice one of these equations involves x, y, and z. That's going to be more complicated to deal with. But one of them just involves x and y. So one of them only involves two variables. That's good. You always want to look for that. Simpler to deal with first. And for those two variables, notice we have a sine-cos relationship. In other words, we have something resembling the rule, which we all know, sine squared t plus cos squared t equals 1. Not exactly, but similar to that, right? We have a variable squared plus a variable squared equals a constant. So here we have x squared plus y squared equals 4. So if we were to say x is cos t and y is sine t, then that would always satisfy x squared plus y squared equals 1. But here we have 4. So is there something we can multiply cos t and sine t by so that this is always true? Tempting? Tempting? Common mistake, Nicholas? Not quite, though, because we're squaring it, right? So if we let x be 2 cos t, y be 2 sine t, and if you want, you can let x be 2 sine t, y be 2 cos t. It doesn't matter, it would still satisfy the relationship. They would just give different parameterizations. They would, in fact, just change the direction we're going along this curve, but it's neither here nor there. So if we let x be 2 cos t, y be 2 sine t, when you square x, you get 4 cos squared. When you square y, you get 4 sine squared. 4 cos squared plus 4 sine squared is always equal to 4. Right? So there's a sine cos relationship here. A variable squared plus a variable squared equals a constant. So usually you're going to let one be cos, one be sine, and then you just have to figure out what you need to multiply them by so that you get this. So one way to parameterize this is to let x be 2 cos t, y be 2 sine t. But like I said, you could say x is 2 sine t, y is 2 cos t. There are infinitely many ways to do this, but this is one easy way that works. So we found something just involving 2 of the variables, we found the sine cos relationship. So if we let x be 2 cos t, y be 2 sine t, this equation is always satisfied. Cool. So we figure out x and y. Now we just need to figure out z. And so to figure out z, we go to the other equation, which involves z. And we get z by itself. So when we get z by itself, we see z is equal to x squared minus y squared plus 1. But we're parameterizing our curve. We don't want anything involving x and y. We want a function of t, right? So we substitute what we already decided for x and y in here and plug it in. When we do that, we get z is equal to x squared, which is 2 cos t, squared, minus y squared, which is 2 sine t, squared, plus 1. And you can leave it like that, or you can write it as, 4 cos squared t minus 4 sine squared t plus 1. So this is a perfectly valid way of writing your parameterization, but I'm going to go ahead and write it in vector form because it's good to get used to doing that. So the vector function, r of t, is just the first component is x of t, which we said was, 2 cos t. Y is the second component, which we said is 2 sine t. And z we said is 4 cos squared t minus 4 sine squared t plus 1. No. So I would careful. Don't use x in this case. So what do you mean exactly, Terrell?
I was just looking at right. So we from the one that only had that involved two variables, the x squared plus y squared is equal to 4, and then we called x is equal to 2 cosine of t. Sorry, I meant to put t, not x, but
Gotcha.
right, we just called it cosine of t, correct, to parameterize it. So could we have called like x to sine of t and y to cosine of t?
Yeah, absolutely.
Okay.
They would still always satisfy that equation.
But that's what we're looking for, is
just a
that
different
cosine of t.
parameterization. So all that's going to do is kind of change the direction you're moving along the curve.
Okay.
But that is a perfectly valid parameterization. The only thing to keep in mind is if you say x is 2 sine t, y is 2 cos t, then you need to just use whatever you used for z.
Right, and plug
That's
it into
change
z.
what z is, but that's still a perfectly valid way to do that. Yes.
Okay, cool. And then we get that 2 from the 4, right? Because we're taking,
Correct.
are we taking like the square root of that? And so if it was equal to 5, what we say square root of 5 times cosine of t.
Exactly. Yeah. So if you have x squared plus y squared equals a number, then you just let x be square root of that number, cos t, and y be square root of that number, sine t, basically.
Awesome. Okay.
Yeah. Okay. So that's sort of strategy 1. For both of these, you're going to find one of the equations. Sometimes they both only involve 2 variables, but you're going to find an equation, the surface involving just 2 variables. And in the first instance, those 2 variables have a sine cos relationship, right? You have 1 squared plus another squared equals a constant. So that's the first strategy, is a sine cos relationship between a couple variables, and then plug in for the other one. The second one is basically you can, and on the equation of one of the surfaces, you can get one of the variables by itself. So for example, suppose we had x minus z squared equals 3. Sorry, let me write this out. So we want to parameterize the intersection. Thank you. Of the surfaces. So x squared, sorry, no, x minus z squared equals, oh my God, go away, 3 is one of the surfaces, and the other is the plane, 3x plus y minus 2z equals 4, let's say.
So do both approaches work, like for the same problem? Like could this approach have worked?
Usually you'll be able to use one or the other. If you can, if for some reason you can apply both, I would usually do the sine cos one. I think that's usually going to be the easiest. If you can do sine cos, do sine cos. But usually it's going to be like either or.
Okay.
But like for instance, in this one, there's no sine cos relationship between any variables. Okay. So we do the same thing. We find the equation which only involves 2. Sometimes there will be, they both will only involve 2. But usually there's a simplest one you can choose. But not always. Sometimes there are multiple options. So this is nice. It only involves 2 variables. And so we can get a relationship between those 2 variables and then figure out the third variable from the other equation. Okay, so notice in this one, we have x minus z squared equals 3. we can get one of the variables by itself and write it in terms of another variable. Right, so we got x by itself. We said x is equal to something involving z. All right, so x is going to be the simple guy here. Z is the complicated guy, right? The term involving more complicated stuff, the variable. So in this case, we get one of the variables by itself, write in terms of another variable. You let the complicated guy be t. Right? Super simple. So we just let z be t, because z is a complicated guy here, right? We have x is equal to z squared plus 3. Like I said, there are infinitely many ways to do this, but this is a really simple one. So if we let z be t, that tells us exactly what x has to be. X is z squared plus 3. If z is t, then that is t squared plus 3. Right. So in both of these, you're going to find one of the equations which only involves two variables, and either you're going to get one of them variables by itself, or you're going to or there's going to be a sine cos relationship. Y is equal to t because because we can, basically, because it's really simple. If you just let z be t, then since you have x by itself, you just replace z with t, and then that's what you get. We let z be like the simplest function we can think of, essentially. That's the idea. So then we need to figure out y. So we go to the other equation, we get y by itself. We get y is equal to negative 3x plus 2z plus 4. And so then making these substitutions, which we already said, because this is a common mistake. When you do a parameterization, you don't want to see x, y, or z anywhere in the functions, right? You need to replace them with expressions in t. So then making the substitution, we get negative 3. X is t squared plus 3 plus 2 z, but z is t, plus 4. And you can clean that up if you want, but that is perfectly fine. So negative 3t squared plus 2t. So minus 9 plus 4 is minus 5. And so we have our parameterization of our curve of intersection. We have x, y, and z, which is fine to leave it like that, but I'm going to write it in this form. So we said x was t squared plus 3. Y was negative 3t squared plus 2t minus 5. And z was t. So remember, when you write the vector form of the parameterization, the first component is just going to give you x in terms of t. The second component is going to give you y in terms of t, and the third is going to give you z in terms of t. It's useful to be able to go back and forth between this vector representation and this representation of the parameterization. Okay, so just to review, curves of intersection. It doesn't always have to work out like this for the surfaces, but usually all the examples we're going to give you will. So in both cases, you look for an equation of a surface, one of the two, which only involves two variables. And you're going to figure out those two variables first. All right. So the first one is one of the equations involves just two variables, and there's a sine cos relationship, right? Variable squared plus a variable squared equals a number. In that case, you just do square root of the number cos t for one of them and square root of the number sine t for the other. Doesn't matter which is which, but you need to keep them straight. And then and then you go to the other equation, get the third variable, which you don't know yet, by itself, and then substitute what you figured out for the first two variables. Back to the other slide, you mean this one?
Yes.
Okay. So that's the first strategy, is find a sine cos relationship between two of the variables, and then solve for the third by substituting. The second is, I would always do that one if you have the option, if there's a sine cos relationship between two variables. The third one is, or the second strategy is, one of the equations involves only two variables, and in that equation, you can get one of the variables by itself. Right.
So what's the R of t equation for this one that we just did? Oh, there we go. Okay.
Yeah. So for this one, you get that variable by itself, write it. So in this case, it was x, get x by itself. So for instance, if we're like 2x, don't write 2x, write x and then divide both sides by 2. But get one of the variables by itself, write it in terms of the other variable, the more complicated thing. Let that complicated variable be t, because we can. And then when you substitute in t, that tells you what the variable you got by itself is. And so that solves for two of them, and then go to the other equation to and make your substitutions to solve for the third unknown variable. All right. Any questions about that? Okay. And just as so there's a question in the homework. Which talks about, it gives you two curves, it parameterizes two curves, and it asks you to say whether they collide. So if you have a particle moving along, so a particle moving along one curve, according to parameterization, and particle moving along another curve, according to a different parameterization. So you want to know if those two, if the curves intersect, or if the particles collide at some point. So two curves intersect. So suppose we have, okay, one curve parameterized by one vector function, say R1 of t, and the other is given by a different vector function, R2 of t. So the two curves intersect if they share a point. In other words, they share a point if at one time t, say t1, the particle on the first guy is at that point, and at some different time t2, the particle from the other guy is also at that same point. So say possibly different times. So times t1 and t2, we're at time t1 on the first guy, we're at the same point as we are at time t2 on the second guy. Right? So here's our first curve, here's our second curve. The two curves intersect. That means at some time t1, I'm at that point on the first curve, and at some possibly different time t2, I'm also at that point on the second curve. Right? The times don't have to be the same to intersect. We say the paths collide if you can find some time t where they're at the same point. Right, so they intersect, so that the paths could intersect, right? So you could go along some path and intersect the path of someone else and not necessarily meet at the same place at the same time. It just means at some point you're here, and at another point, the other person was also there. You say you collide if you end up at the same place at the same time. So that's stricter, right? So there's a single value of t where both paths are at the same point. Does that make sense? Not going to do an example, but that's what that means. And then finally, I want to do one quick example, because this will be useful. So suppose we have an ellipse which lies in the xy plane. So we're in space, but we're in the plane z equals 0, the xy plane. So if you were to write the equation of this in the xy plane, say we had like x squared plus y squared over 4. So consider this ellipse here, right? So we go 1 in the x direction, 2 in the y direction. Remember, that's how we do ellipses, right? So that lies in the xy plane, which is the plane z equals 0. So suppose we want to parameterize this curve. So this lies in the xy plane, so that means the z coordinate is always going to be 0, right? Z is always equal to 0. And x and y satisfy x squared plus y squared over 4 equals 1. So notice this is almost x squared plus y squared equals 1, which would be sine squared plus cos squared equals 1, but not quite. So let's let x be cos t. What can we do to y? So we want to have cos squared plus sine squared equals 1. So if x is cos t, we have cos squared. How do we make y squared over 4 equal to sine squared? So what can we square so that when we divide it by 4, we get sine squared? So we want whatever that is divided by 4 to be sine squared of t. Well then, whatever that is multiply both sides by 4 sine squared t. And so if we just let y be 2 sine t, when we square it and divide it by 4, we get sine squared. So we'll let x be cos t, y be 2 sine t, z be 0. That's going to parameterize this ellipse in the xy plane. So take note of that. That's useful to know how to do that. Okay. Suppose we want to move the center from, so it's centered at the origin, 0, 0. Suppose we want to move the center to the point 1, 2, 3. So what we want to do is basically we want to move the center to the point 1, 2, 3. So 0, 0, 0 is going to move to 1, 2, 3. So basically just take your parameterization, add to it 1, 2, 3. So we get cos t, 2 sine t, 0, plus the vector 1, 2, 3. So basically, you're just taking every point you're moving it, 1 in the x direction, 2 in the y direction, 3 in the z direction. And so you could leave it like that, or you could add component by component. So we get x is cos t plus 1, y is 2 sine t plus 2, and z is 0 plus 3, which is 3. So this tells you how to parameterize that ellipse in the xy plane, and then take that ellipse and move the center to a different point, 1, 2, 3. Basically, you just add the position vector for that point for the center. Okay, any questions about anything we've gone over today?
So we just called y is equal to 2 sine of t just to satisfy that x squared plus y squared over 4 is equal to 1, right? Because we called x cosine of t, but we had to put the 2 because that's like 1/4 to cancel the, okay.
Right, yeah. So there are infinitely many ways to parameterize, but this is the easiest one. We can find a way so that we can get a sine cos relationship here. And that's what we did. Yeah, correct. Any other questions? So why do I need to include 0 in the vector if it's not included in the problem? So what I want to do is I want to parameterize this circle or this ellipse in space, right? So I say it's the ellipse, if you write the equation of it in the xy plane, that's the equation. But I say it's in the xy plane, it's in space, right? So if we're parameterizing something in space, we need to say what the z coordinate is equal to. Z needs to be a function of t also. Well, if you lie in the xy plane, you're always in, like the z coordinate of every point in the xy plane is 0. Right. So for parameterizing in space, you have to set z equal to 0 because that's always the case for all the points on this ellipse. Does that make sense? So if you can parameterize things in 2 dimensions, right? So then it would just be a 2-dimensional one. If you just wanted the guy in the xy plane, it would be so cos t 2 sine t. If you want it, x is equal to cos t, y is equal to 2 sine t. But we're doing this for a curve in space in this case. So we need to say what's happening with the z coordinate as well. Okay, sorry, went over a teensy bit, but that's it for the chapter. So if you don't have any questions, then I will see you guys on Monday. Have a great weekend. And
quick question.
yes.
Not really a question. Just could you go back to the slide that has two curves given by R1 and R2 intersect?
Yes.
Thank you. All right, I'm all good then.
Okay. All right. Have a good one, guys.